Hello, Stuart. Thank you so much for your time for the interview.
Yeah, it's great to be here.
Yeah, thank you, and for the talk. It was a great talk. So I had a couple of questions for you. So you've worked with C-star algebras for a long time now. What makes these objects so interesting, and what are they?
I guess I got interested in because I sort of like the blend of analysis and algebra. So it's a sort of place where these two subjects come together. So what are they? There's a formal definition. There's a sort of the Banach star algebras with somehow a key identity which sort of really forces the analysis and algebra to interact nicely. But I sort of think of them as where you would uncover them sort of as a master's student or a graduate student. It's you've enjoyed the spectral theory for bounded operators on Hilbert space and want to know what the right abstract framework where this fits in. This leads you to the theory of first commutative Banach algebras and then to C-star algebras. And somehow what you discover with C-star algebras is they also have this sort of deep connection to topology through the fact that the commutative C-star algebras arise as continuous functions on spaces. And it's at this point, I think, for me, that I sort of realized that there is a sort of blend of many things I enjoy about mathematics coming together in one place. And that's why I got interested in them.
I see. So this blend that you're talking about, so this topology and algebra and analysis, all these different areas, what's the area of that is remembered more or is used more in C-star algebras?
I think this depends on the problem, right? So this is like I think the nice thing about it, if you're studying things around K-theory, then you're sort of doing something that's sort of non-commutative algebraic topology. But maybe if you're studying things around dimension theory, real rank zeros, table rank, this is sort of a non-commutative version of Lebesgue covering dimension. And then, one finds yourself sort of doing things that are more, approximation theory when you're sort of looking to model algebras through finite dimensions, completely positive maths, which has sort of connections to areas like quantum information theory. So it's this sort of the place where things come together. I mean, when I got into operator algebras because I sort of really liked sort of abstract analysis I was studying. I hadn't really realized that in this direction, I'd be finding myself doing a lot of things connecting to groups and group actions, but this is a very pleasant surprise. I sort of realized it. 20 years, what an important sort of source of motivating examples this was.
Yes.
But I mean, different, and it's the sort of the nice thing about it, different takes on the, different directions or different questions, as you'll know yourself. Sometimes you find yourself looking at sort of things coming from coarse geometry, but sometimes you find yourself looking at things coming from a more analytical perspective.
Yes. So from the point of view of a PhD student, of somebody that is about to start a PhD, it might be daunting. It might be a bit overwhelming to somehow go into this field. Do you think it's needed to know your ways around algebra and topology and analysis very well, or do you think you can more or less focus on one of these and deal with the questions that are
I certainly didn't. I mean, I went into operator algebras because I sort of liked my functional analysis, the work I'd done in functional analysis, and I found myself learning various bits of topology and algebra along the way. So I think it's sort of normal to come into this thing, so, you sort of like something, and then you find, okay, you study some more in that direction, then you have to be open to becoming broader during your PhD, picking up other skills that you didn't have when you started. And I very much encourage my students to do this. But it's very normal for me to take on a student actually who has, sort of where I was and found themselves, okay, well, I've enjoyed all of the work I've done so far in functional analysis, and this is a natural next stepping stone. So you can come at this from many different directions. You could come in knowing you sort of liked non-commutative geometry, for example, and wanted to understand the basic building tools better, or you could come in from a sort of a direction of saying, okay, well, I've enjoyed studying operators on Hilbert spaces, and how does this become more abstract?
Well, that's very good. And which idea do you think, or which theorem of yours is your favorite, or you think the most influential in your work?
I don't like to have favourites.
Okay, fair enough.
and I don't want to really talk so much about my own work either. But
okay,
but I guess I'd like to sort of emphasize something I think it was a big thing over my career as it developed, was this sort of connection that's re-emerged over the last 10 to 15 years between two different branches of operator algebras. Because, I mean, there's C-star algebras and there's von Neumann algebras, and if you were back, if we were casting ourselves back 50 years ago, there would have been one subject. There would have been, most conferences would have been a conference on operator algebras. And then, as inevitably has happened in mathematics, the technical difficulty of mathematics everywhere means that it gets sort of more spread out.
Yes.
And what has really happened over the last 10 years is that these subjects have sort of come back together and there's interplay in both directions. Over the last 10 years, I think we've seen quite a lot of use of von Neumann ideas and C-star algebras, but before that also work of Ozawa, for example, which I found really inspirational, using sort of C-star algebra, group C-star algebraic methods to make progress in von Neumann algebra. So it's like as a concept, I find this sort of idea of the interplay between non-commutative measure theory and non-commutative topology really, really fascinating. And it sort of suited my own mathematical direction, because I started out in von Neumann algebras a long time ago and as a PhD student, and actually found myself transitioning to something more topological as I went. So when I remember hearing some talks in around 2010 where Nate Brown in particular was making this connection more explicit, and it really enabled me to think, yes, I could do something here. Whereas previously I hadn't seen how my sort of von Neumann expertise would be useful to this activity that was going on. So this really excited me.
Okay. And is this interplay between the more measure theoretic side, the more von Neumann side, and the more C-star side, is that interplay gonna play an important role in the future, do you think, or is it somehow a fountain that is now dry?
I hope so.
Okay.
But the downside of these interviews of being recorded, making predictions about the future, you can all look and find out whether I was right or not.
Yes.
One of the things that, after Kohn proved his fabulous classification of von Neumann algebras coming from his work on injectivity implies hyperfiniteness, the next sort of 10 years saw a huge amount of progress. A classic example is Ognyanu's classification of all actions, the uniqueness of outer actions of, say, amenable groups on injective factors. And then only last year, maybe 2 years ago, we started to see really C-star algebraic versions of this through the work of Jamie Gabe and Gabor Szabo. So I sort of imagine that there's a potential for this sort of really to grow outwards as opposed to be sort of a culminating stage. But we'll see. I mean, the exciting thing about mathematical research is every time I've sort of found myself asking, sort of predicting what will happen over the next 5 years, if you actually look back, it's not often that you're right.
Yes, So if you had to recommend a topic or for a PhD student that you think is going to probably, that some idea or some theorem that they should know only because of the ideas behind the proof or because it somehow encapsulates a lot of research in the area, what would it be?
I really like, the famed theorem I mentioned about Jamie Gabe and Gabor Szabo is a really good example of this, but I also really like, I was astounded in sort of 2017, 2018 when Chris Schaffhauser showed how to prove a theorem I'd been involved in a much more elementary and straightforward way. And this, Chris's sort of abstract approach has really, I think, been quite game-changing in how we approach the field today. So I certainly try to persuade a lot of my students to read and understand these papers of Chris and take things from there. But I think the exciting thing about the subject now is that there's many different directions. So there's this huge body of work, for example, on group actions and the fundamental papers by David Kerr, and you certainly understanding these properly would be certainly something I would also advise. And then so being forced to choose is difficult. We shouldn't play favourites. There's been a huge amount of really exciting work.
That's a problem of the field. I think that there's such a huge amount of work that it's difficult to choose. And Lastly, with regards to the future, so this interplay or this paper of Jamie Gabe and Gabor Szabo that you mentioned, is there any other branch of mathematics, of C-star algebra, say groupoids or maybe coarse geometry, that you think is going to at some point play an important role? Or do you, I mean, it would become perfectly understandable to not want to answer such a question. I mean, this is not...
I think the exciting thing at the moment is the many different connections that are being made. So I found another striking paper, which is the rigidity theorem for row algebras by a team of 5 people. And it's a really striking result from 2021, I guess, which I would really not have predicted in that level of generality. And there's now, because of this, you get very interesting questions. Okay, well, this C-star construction remembers all of the underlying coarse geometry.
Yes.
So how does it do so? How do you actually read the data back off? And I think that the same will be true also for sort of questions around classification.
I see.
How do you get access to this data given that it is there? In other directions, I think there's really potential for a lot of progress on sort of C-star versions of sort of modern C-star versions of subfactor theory and actions of tensor categories on C-star algebras. It's something I've been promoting for quite some time, but I feel it's something that is sort of now possible in a way that maybe 3-4 years ago was not through this sort of lens of von Neumann algebras. But I mean, if you look back over the last 10 years, the subject has sort of seen many of these dramatic advances that would have been hard to predict. So it is really hard to predict where we will be in 10 years' time.
Yes.
That's what's so exciting, actually, about the current research environment.
Okay. Yeah, well, I'm glad we both find it so exciting. That's all for today. And thank you so much.